Okay, students, now we'll talk about the last required section in this chapter, which is the period of the mass that attached with a spring. If we have a spring with constant K and a mass M, we make this system vibrating. If we pull or push the mass and leave it, then it will start oscillating. Okay, now we know that from before that omega is equal to 2 pi over the period. This section, to compute the period we can reorder it. Period is equal to 2 pi over omega. For this system, we will not go to derive this relation. Omega is equal to the root of K over M. Okay, omega is equal to the root of K over M. If K is big, then omega will be big. If M is big, then omega will be small. So we just need to put this omega here. Omega is equal to 2 pi over T, which is equal to the root K over M. Take the inverse, yes. Then T over 2 pi is equal 1 over the root K over M. Order it, reorder it, then T is equal to 2 pi. We can take the inverse of this, which will be the root of M over K. This is the period for this system. It is a simple formula. You will face that in the lab, the final lab, I think, simple harmonic oscillation. Now I need just to show you some spring mass systems and how we can find the K equivalent for this system. We will not use it, but I need you to know about it because you will face that in the lab. If you have two not parallel, these are series mass springs with K1, K2, then the equivalent constant K, 1 over it, is equal to 1 over K1 plus 1 over K2. The equivalent K constant, it will be less than both of them. If we have two parallel spring with K1 and K2, then the equivalent constant for this system is K1 plus K2. Then it is more difficult to pull or push this mass because we have two springs. For this system, the mass is hanged with two springs. It is the same as parallel. So the equivalent constant, it will be equal to the first constant and the second constant. Look, if we have a series system, then it will be 1 over the equivalent. If we have parallel and parallel, because we have two connection points here, we have two connection points here, then this is parallel. We have two connections, then this is parallel. We have just one connection here, it is in series. Okay, this is just to know if we have more than one system spring in our system. We don't need to use them a lot, just once in the lab. What if we need to solve an example on this formula? T is equal to 2 pi for multiplied by the root M over K. For any one of these systems, if the mass is 5 kilograms, if the spring constant is 100 Newton per meter, then find T. Okay, it's easy. T is equal to 2 pi M over K under the root. Put the numerical values, then T is equal to 1.4 seconds. That's all for this section. That's all for this chapter. Solve questions and examples about this one and meet you in the next chapter. Thank you.